Chemical bonding, bond energy and bond lengths. In this tutorial, we will be going over why do elements form chemical bonds, bond enthalpy, otherwise known as bond energy, using average bond enthalpies to estimate enthalpy changes for reactions, the relationship between average bond length and average bond enthalpy, and finally some worked examples at the end. Bond energy and bond lengths. Why do elements form chemical bonds? When two atoms approach each other, the electrons of one atom are attracted to the nucleus of the other atom according to Coulomb's law. At the same time, the electrons of each atom repel the electrons of the other, and the nucleus of each atom repels the nucleus of the other. Chemical bonds will form if the system can lower its overall potential energy. In a bond between two hydrogen atoms, the system will act to minimize the sum of the positive or repulsive energy terms and the negative attractive energy term. The distance where the energy is minimal is called the bond length. So here, at the very beginning, when two hydrogen atoms, so hydrogen 1 and hydrogen 2, are approaching each other, there's no overlap, no attraction. When they start coming together at the bottom of this potential energy curve, where we are definitely negative, there is some overlap and some attraction. But if these two hydrogen atoms get too close to each other, we start experiencing repulsion. And later on in the next video, we will explore these models in more detail and talk about the bond length, which we can see outlined right here, and the bond energy, as we can see in this section of this model here. The bond enthalpy of a chemical bond is the energy required to break 1 mole of the bonds in the gas phase. So for example, hydrogen. Diatomic hydrogen in the gaseous phase is broken into 2 hydrogen atoms. The bond enthalpy, or delta H, is positive 436 kilojoules per mole. So as we can see from this model here at the bottom, a diatomic hydrogen molecule needs 436 kilojoules of energy per 1 mole to break those hydrogen atoms apart and form individual gaseous hydrogen atoms. Consider the molecule methane. Methane has 4 carbon to hydrogen bonds, each with a different bond enthalpy. So methane in the gaseous state, if we remove 1 hydrogen and it becomes CH3 and then 1 hydrogen atom by itself, that requires 460 kilojoules of energy. If we take that CH3 and we remove another hydrogen atom with a resulting CH2, that has a different bond energy associated with it. So an average bond enthalpy, or an average bond energy for a chemical bond, is an average of the bond energy values for that bond in a large number of compounds, which is really good for us when we have to start doing these calculations in the future. Bond enthalpies depend on the kind of atoms involved in the bond and the type of bond. Are you dealing with a single, a double, or a triple bond? In order to break a chemical bond, energy must be absorbed by the system from the surroundings. Breaking a chemical bond is an endothermic process with a positive enthalpy change of positive delta H. In general, for a given pair of atoms, triple bonds are stronger than double bonds, which are in turn stronger than single bonds. In order to form a bond, energy must be released by the system to the surroundings. Forming a chemical bond is an exothermic process with a negative enthalpy change, negative delta H. The greater the bond enthalpy, the stronger the resulting bond. Molecules with stronger chemical bonds have less of a tendency to undergo chemical changes. So we can see these in these bond enthalpy values here on the bottom. A nitrogen molecule with a triple bond has a bond enthalpy value of 946 kilojoules per mole. Diatomic oxygen is 498 kilojoules per mole, and a single bond in diatomic fluorine has a bond enthalpy value of 159 kilojoules per mole. Average bond enthalpies can be used to estimate the enthalpy change of a reaction. Bond enthalpies allow predictions of whether a given reaction will be endothermic or exothermic. To figure out the enthalpy of a reaction, we're going to take the sum of the bond enthalpies of bonds broken minus the sum of the bond enthalpies of the bonds formed. So again, let me say that. It's going to be bonds broken minus bonds formed. A reaction is exothermic when weak bonds break and strong bonds form, and a reaction is endothermic when strong bonds break and weak bonds form. Using bond enthalpies to calculate delta H of reaction. So we have a chemical reaction here. Methane plus fluorine gas yields fluoromethane and hydrogen fluoride gas. You should be able to write out this chemical reaction and balance it. And if you do it correctly, you should get CH4, which represents methane, F2, which represents the fluorine gas, CH3F, which represents the fluoromethane, and HF, which represents the hydrogen fluoride gas. Now, this is already balanced, which is great for us. So let's look at some of the structures that represent each part of the reaction. So we have methane, we have diatomic fluorine, which is undergoing a reaction to produce fluoromethane and hydrogen fluoride. So what we need to do here is figure out what bonds are broken and what bonds are formed as we go from reactants to products. So in order to achieve CH3F, that means we have to break one of these CH bonds. It also means that we need to break this single bond between the fluorine atoms. So for bonds broken, we're going to have 1 mole of CH and 1 mole of FF. Now for bonds formed, because we're removing this H and basically breaking apart this F, this H is going to bond to one of these F's, and this F is going to take the place of this H, which means we are forming this bond and we are forming this bond. So bonds formed, 1 mole of CF and 1 mole of HF. And drawing out these structures to see what exactly you are breaking and what exactly you are forming is highly encouraged. So we are given 1 mole of CH and 1 mole of FF being broken, and 1 mole of CF and 1 mole of HF being formed. Then you would look up these values using your textbook of the bond enthalpies for each of our situations, and then what you are going to do is you're going to take the sum of the bonds broken minus the sum of the bonds formed. So if we wrote this out, we'd have 1 mole of CH, 1 mole of FF, and these are my bonds being broken. And then we'd have 1 mole of CF and 1 mole of HF being formed. Once I have this initial setup written out, then what I would do is I would substitute each one of these values in for each one of these bonds, and I would get 414 representing the CH, the 159 representing the FF, the 485 representing the CF, and the 565 representing the HF. Then I would do the math associated with it. So the amount of energy associated with bonds being broken is equal to 573 kilojoules per mole, and the amount of energy associated with the bonds being formed is 1050 kilojoules per mole, for a total of negative 477 kilojoules per mole, meaning that this is an exothermic reaction. Let's do another example. Determine the enthalpy change for a reaction where nitrogen gas reacts with hydrogen gas to produce ammonia gas. So the reaction that you should be writing out should look like this. N2 plus 3H2 yields 2NH3. Notice that we now have coefficients as part of our reaction. So if we were to draw out the structures associated with this, we'd have one diatomic nitrogen molecule plus 3 hydrogen molecules to produce 2 ammonia molecules. So when we talk about bonds being broken, we will need to break this triple bond between the two nitrogens. We will need to break all 3 of these single bonds between the hydrogens. Then when we talk about bonds being formed, we will have to form each of the bonds in both of the ammonia molecules. So we're going to have to form 1, 2, 3, 4, 5, 6 bonds between hydrogen and nitrogen. So bonds broken will be 1 mole of diatomic nitrogen and 3 moles of diatomic hydrogen, and then bonds being formed are going to be 6 moles of nitrogen bonding to hydrogen. So we have our summary here of bonds broken and bonds formed. We have our given values from the textbook that you are using, and then we're going to write out the reaction showing bonds broken versus bonds formed. So we're going to break 1 mole of diatomic nitrogen and 3 moles of diatomic hydrogen, and then we're going to form 6 moles of nitrogen bonding to hydrogen. So again, after we have this skeleton outlined, we are going to substitute in our values, and then we're going to calculate the amount of energy associated with bonds being broken versus bonds being formed to give us our overall delta H of reaction of negative 80 kilojoules per mole. So what did you learn in this tutorial? We talked about why do elements form chemical bonds. We talked about the idea of bond enthalpy, otherwise known as bond energy, using average bond enthalpies to estimate enthalpy changes for reactions, the relationship between average bond length and average bond enthalpy, and finally we did some worked examples at the end. Need more help? Feel free to contact me. Have a great day.